Does it show up? Good. Cool. Okay. Thanks everybody for coming. Welcome to Astronaut. We're very, very happy to have all of you here. So my name is Carolina. I'm the program administrator for TSI and your moderator for the evening because your usual moderator is the speaker. Right. So a few reminders before we get started. Oh, that's your talk. Oh, wrong talk. So, okay, so a few reminders. So like I said, TSI and Astro McGill are committed to equity, diversity, and inclusion. So we can only share Astro awesomeness with all of you if everyone feels safe and welcome. So if you have any concerns, you're feeling uncomfortable at any time, both like in person or online, just feel free to send us an email. We'll be happy to help. And just take a moment to familiarize yourself with our code of conduct, kind of like the behaviors that are acceptable and unacceptable. But yeah, again, if you have any questions, don't hesitate to reach out to any of us. So before we get started with the actual talk this evening, we have one more thing that we'd like to draw your attention to. So we currently have 2 fundraisers that are going on in the Department of Physics. Graduate students like Hannah. So graduate students like Hannah are the real engines of teaching in our department, and we strongly feel that they deserve all the recognition they can get. So we are fundraising for the Edith Engelberg Graduate Teaching Award. Edith Engelberg was a real pillar in our department's teaching for decades, and we can think of no better way to honor her legacy than by funding the Grad Student Award in her name. If you go to this QR code, you can make a donation and learn more about the award as well. And there's also a cash box, I think, outside that you can make a donation to. Every dollar counts, even if it's like just like $1, that's absolutely fine. We're happy to take donations in any way you can spare them. And like I said, we have another fundraiser too. So of course, grad students were once undergrads, and one of the ways we can increase the representation of in our graduate student population is to provide undergraduate research opportunities. Our second fundraiser is for BIPOC students, which is Black, Indigenous people of color. With this fundraiser, we can hope to increase the number of opportunities for underrepresented students to gain research experience in our labs over the summer. This can be a real leg up for students who are interested in pursuing careers in physics. So again, if you're interested in donating, you can the QR code is right here. And yeah, anything you can spare, and goes a long way towards making these awards possible. So without further ado, it is my pleasure to welcome tonight's speaker, Hannah Fronenberg. So Hannah is a PhD student here at TSI and the McGill Department of Physics. She worked with Professor Adrian Liu on 21-centimeter cosmology, studying cosmic dawn and reionization. She's also our outreach coordinator here at TSI. And as usual, your moderator for these events. After the talks, we'll have a Q&A period where you'll have the chance to ask your most pressing questions about tonight's talk. For those of you joining on YouTube, you can just type your questions in the chat and we'll pass them on to Hannah. So without further delay, Hannah, you have the floor.
Okay. Thank you, Carol. So this is really weird that I'm in this other position tonight. So yes, let me just get my cursor back. All right. So yes, tonight's talk is titled, "Did the Big Bang Really Happen?" So did it really happen? Has anyone here ever heard that it did not happen? But not in the Earth is only 6,000 years old sort of thing. in the science way. Has anyone heard that the Big Bang didn't happen? Few. Okay. So maybe we'll get to some of those ideas tonight, but I will admit to you at the start that the Big Bang is actually not the full story. It's part of the story, maybe, but it's not a complete theory. And there are some serious problems with this theory that need to be solved. That being said, this is an extremely good start, without a question. So first, let's just revisit what the Big Bang Theory even says, and then maybe we can start to see some of the problems with it, and hopefully look at a few solutions. So what is the Big Bang Theory? This is the picture of the universe that it gives us. So time moves along this direction. The beginning is over here. Today we live over there. And the universe started in a very dense, infinitely dense, hot place. It then expanded into this period where, for the first time, particles formed. Those particles then came together to form the first ever atomic nuclei. And you can see that it's kind of this like burnt orange color, because just like a cloud of fog, where the light rays are always scattering through the individual molecules in the cloud, it was like an opaque cloud of particles and light particles, photons. Soon, the universe expanded just enough and was therefore allowed to cool just enough for the first actual atoms to form. So those first atomic nuclei got their electron buddies. Then a very special thing happened that caused a very special event called the cosmic microwave background, which we'll discuss later. We entered a period of the dark ages, the cosmic dark ages, where nothing existed in the universe except individual atoms floating around. The largest thing in the universe was an individual atom. But slowly but surely, those atoms came together to form the first stars, and those stars came together to form the first galaxies, and eventually we end up with the galaxy-filled universe that we know and love today. So the Big Bang Theory predicts that we live in an expanding, homogeneous, and isotropic universe. So let's go through each of those things one by one, because these are the fundamental concepts that describe the supposed universe that we live in. Excuse me. So first, expanding. Some of you may have seen this depiction before, but what does it mean for our universe to expand? So all of the stuff in our universe, all of the galaxies, all of the stars, all of the stuff made of matter lives on a cosmic stage that we call spacetime. So this balloon here is depicting spacetime. And you can imagine that all of the galaxies that exist in our universe are stickers that we've stuck onto the balloon. And the way expansion works is that as we blow up the balloon, we can see that these stickers that are stuck on the balloon move further and further apart from one another. The stickers themselves, they're made out of something else. They're made out of paper. They're stuck onto the balloon. They don't expand, but they get separated through blowing up this balloon. So that's the type of expansion that exists in our universe. Another question. Well, okay. First, how do we know it's expanding? So this theory posits that the universe is expanding. How do we know it's expanding? Well,
there's nothing flying.
Did someone? No? Okay. So how do we know that it's expanding? Well, some people made some very special measurements, and they're listed just there in the corner. That when you look at galaxies, the further away a galaxy is, the faster it is moving away from you. So plotted here, we have the velocity at which the galaxy is moving away from us, and then the distance between us and the galaxy. And we see that galaxies close by move away from us slowly. Galaxies further away move away from us quickly. So if we study this relationship, which is what these people did, we can develop a relationship, a mathematical relationship between this recessional velocity of galaxies and the distance they are from us. And this slope of this line, which is denoted by this letter H naught, is Hubble's constant, which tells us what the current expansion rate of our universe is. Okay, so we know it's expanding. Now, I want to address two common questions about expansion that I often get. So the first one is that if we live in space-time, if the stage that we're living on is space-time, and we say that space is expanding, is time also expanding? And the answer to that is no. In fact, only the spatial components of our universe are expanding. Time remains the same. All right. Next question that I often get about expansion is, what is the universe expanding into? Who's that? And anyone, I hear some laughs. Has anyone ever wondered this? Like, doesn't it have to be expanding into something? Like the balloon blows up and it's like taking up the air that used to be there. So this is a difficult one. So I brought some gadgets with me to try to explain this concept. And it really comes down to, is our universe embedded in some higher dimensional space that it's expanding into? So geometries or spaces have both, or can have both, intrinsic and extrinsic properties. So an intrinsic property is a property that is a property of the space in and of itself. Like in its heart of hearts, it has this property. But an extrinsic property is a property that emerges as a result of it being embedded in a higher dimensional space. So geometries have intrinsic properties, regardless of whether they are embedded or not. And then, said differently, these intrinsic properties are completely agnostic to whether the geometry is embedded. Okay, so let's look at some examples. So here I have two different geometries. I have this curved hemisphere, and I have a sheet. So we can ask, what is the intrinsic property of this hemisphere? It's curved. Someone over here, I think, said that. And how do we know that? Well, because no matter how we try to bend it, I can never make this look like a flat sheet. No matter what I do, it is intrinsically curved. Another way to put that is no matter how I bend it, no matter how I embed it, no matter how I embed it in this 3D space, this is always curved. With the sheet, on the other hand, if I bend the sheet, this is not an intrinsic curvature because I can make it flat. It's not always curved. This is not intrinsically curved. The fact that it appears to us curved is an extrinsic property because it's a special way that it looks as a result of being embedded and for us having changed something from the outside, so to speak. All right, so we're almost there. I promise we're almost there. So another way that you can describe it, the difference between intrinsic properties and extrinsic properties, is that intrinsic properties are properties that can be noticed by creatures living in the space. So now let's jump into a one-dimensional universe. Here is my one-dimensional universe. It is a circle. And what I define the circle to be is a closed loop with some fixed length. So what does a creature in this one-dimensional universe experience? You can imagine we have a little creature that lives over here. And let's say every day it gets up, And it can only walk in two directions. It can only walk forward or backward. So every day it gets up and it walks and it does the whole round of its universe. And in some fixed number of steps, it will arrive at the place it started. So that's what it experiences. And so what are the intrinsic properties? What are the properties that the creature can know about? Well, it knows that it lives in a closed universe because it arrives at this place it started every day. And it knows that its universe has a fixed length or a fixed circumference or fixed size. It knows that it will always have a certain number of steps to reach the same point. Now, regardless of how I distort this, the experience to the creature living in this universe is always the same. Even if I bend it like this creature will start at some point, walk in one direction, and in the same number of steps will eventually get back to the place it started. So again, the bending is not an intrinsic property. It's a property that we from the outside can see. It's a cosmetic thing. It's not intrinsic to the space itself. So now, the question is expansion something that can be described intrinsically, or is it a result, is it an emergent property of embedding something in a higher dimensional space? So who thinks, by raising hands, who thinks that expansion is something that emerges as a result of being embedded? No one. Okay, we have a few people. Who thinks that expansion is something intrinsic? Well, a lot of people. So let's check. We have our expanded universe. We have our expanded one-dimensional universe. And so the question is, if this is an intrinsic property of the universe, that means the creature living on the universe could tell that something has changed. Well, would the creature know that its universe expanded?
Yes.
Of course, because it will start here, it will start walking in its usual direction, and after a while, it'll realize, oh my God, why is this loop taking so long today? Why am I not back at the place I started? Every other day, it only took me this long. And of course, the same thing is true for us. We, as creatures from the inside, have measured that our universe is expanding. So indeed, expansion is an intrinsic property of our universe, and it is completely agnostic as to whether it's embedded in some higher dimensional space. You don't need an embedding to talk about expansion. So what is the universe expanding into? It's not even a relevant question. That's not a thing that we need to talk about because it's an intrinsic property. All right, so I hope we all understand expansion now. Next, we said our universe was homogeneous. What that means is that the universe on the largest scales is the same everywhere. So one way you could think of this is if you're walking in a dense forest. And when you walk from one place in the forest to another, you see that the forest generally looks the same from the place you started. Now, that of course doesn't mean that all the trees are identical carbon copies of one another, but just in general, the general landscape looks exactly the same. And that's why people get lost in forests. So the next thing that's special about our universe is that the universe on the largest scales is the same in all directions. The universe, we say, is isotropic. And so if we go back to the forest, that means that if we look around in all directions in this forest, that it looks the same in all directions, such that it's kind of difficult to orient yourself in general. And so it's in this sense that we mean the universe is homogeneous and isotropic. If we zoom all the way out to the largest scales, the universe looks the same everywhere and in all directions. But that doesn't mean that every galaxy is a copy of every other galaxy. It's like a large scale feature. And the technical word that, we use to say that this is like a large scale thing and not the fact that the universe is just copies of individual galaxies is to say that the universe is statistically homogeneous and isotropic. Okay, so we live in an expanding, statistically homogeneous and isotropic universe. Now, a key prediction of the Big Bang Theory is the existence of a homogeneous and isotropic cosmic microwave background, or the CMB. So let's go back to our history of the universe, and let's focus in here on this little slice, this moment where I kind of hinted to earlier was like a really important time. So let's zoom in to see what happened. Again, time still runs. Here is early, and then time is evolving this way. And we see that early on, all there was, some atomic nuclei, considers hydrogen nucleus, helium nucleus, some electrons. And we see what's depicted here as this yellow fog, which is just to say that the universe is so dense that just like a cloud of fog, the light keeps scattering off of these particles and it's opaque. You can't see through it. But eventually, the universe, it keeps expanding and it cools down, and these first atoms start to form. These nuclei trap their electrons, and the universe becomes low density enough that these photons, these light particles, which are depicted in yellow here, can stream freely for the very first time. And so that's the cosmic microwave background. It's this predicted first light that exists in the universe that results from an expanding, cooling, and it should be a homogeneous and isotropic background of glowing light. So how do we check that it's there? Well, luckily, light for us is a time machine. And our ability to know about the universe's past relies on a very important and striking fact, which is that the speed of light is finite. And this is the speed of light. It's very, very fast. It's 300 million meters per second, but it's not infinite. So just a few examples to show this at work. So of course, we don't notice any time delays between when light leaves some object and travels to our eyes. We see things happening pretty much instantaneously. So for example, when you're looking at the computer, it takes 1.6 billionths of a second for that light to come from the computer to your eyes. So it's pretty much instantaneous. If you look at the sun, which I don't recommend, but if you do, what you're seeing is not the sun as it is right now, but the sun as it was 8 minutes ago, because it took light 8 minutes to leave the sun and travel to us and come to our eyes. Now, if we look even further away at this comet galaxy, it takes 3.2 billion years for the light to leave that galaxy, travel all the way to us, and reach our eyes. And of course, that's also the motivation for describing distances in light years, because at a certain point, it's a lot easier to talk about the time it took to travel as a measure of distance than, saying a bajillion, gajillion kilometers. So we can imagine that this is the picture we have. We are at the center, and, we can look away and see what the universe looked like 100 years ago. If we look a little bit further, we can see what the universe looked like 1 million years ago. If we look even further away, we see what the universe looked like 5 billion years ago. And maybe if we look far enough, we can see the first light ever, the cosmic microwave background. And indeed, we look out and see this. This is a map of the sky in the microwave band. And we measure the cosmic microwave background to be the same temperature across the whole sky, 2.725 Kelvin. It's completely homogeneous and isotropic. That's amazing. So we're like, we saw the Big Bang. That's the prediction. But as I said, when I started, there are problems. There are problems with the Big Bang on its own. There's the horizon problem, the structure formation problem, the monopole problem, the flatness problem, the lithium abundance problem, the naked singularity problem. There's a lot of problems. And I could continue, but we only have an hour together. So let's go through some of these problems. All right, we'll start with the horizon problem. So as I said, we measure the CMB and wow, it's the same temperature everywhere. And the technical term for saying that something has the same temperature is to say that it's in thermodynamic equilibrium. And you can kind of, we all have experienced that. You take, a cold cup of water and you have a hot cup of water and you mix the two together. And at first, you're going to have streaks of hot water and streaks of cold water, but eventually all the particles, share energy, and eventually they all become the same temperature. They all reach thermodynamic equilibrium. And so the same must be true for the CMB. But if we look a little closer, we'll realize that there's a problem. So here is kind of, we can imagine as a top-down view of our universe, kind of like the image I showed with the arrows going outward. So we're in the middle in the green dot, and this circle denotes our observable universe, which is the part of the universe that we can see because the time since the Big Bang, there's enough time since the Big Bang such that photons from the region inside the circle can travel to us. So pretty much we're going to say that the CMB is at this surface because it's like 400,000 years after the Big Bang. It's pretty much in the grand scheme of things at the beginning. So now let's look at two different points on each side of our universe. We call this thing, this surface, our horizon. So we look at one side of the universe, okay, it's 2.7 Kelvin. We look at the other side of the universe, okay, it's 2.7 Kelvin. But the thing is that those regions of space too have their own regions of observable universe. And if you look at this, you will see that this orange dot is not inside of the red dot's observable universe. And the red dot is not inside of the orange dot's observable universe, meaning that not enough time has passed for those 2 points to have ever communicated. So because not enough time has passed between the Big Bang and the CMB for the points at the horizon to be in causal contact, how could they possibly be in thermal equilibrium? You need to share information. That's like part of the definition. How can this be? How can it be that we see them in thermal equilibrium, yet they're not in causal contact? That's the horizon problem. Next, we have the structure formation problem. So I said we saw the CMB. It was completely homogeneous and isotropic. I lied. I only lied a little because it's pretty much homogeneous and isotropic, but these hot and cold spots that we see if we look deeper into it are slightly different temperatures. You can imagine this little cold spot here is 2.72547 Kelvin. And this little hot spot is 2.72548 Kelvin. Slightly off. That is the level of difference between the hot and cold spots of the CMB. But it is these differences in temperature that eventually allow all galaxies and all structures in the whole universe to form. Because without some slight differences, if it was completely homogeneous and every atom was exactly perfectly spaced between any other, gravity would never pull any closer to each other. They would be completely gravitationally stable. So these differences are very important. But the Big Bang Theory only predicts a homogeneous and isotropic universe. But we observe our universe to have slight inhomogeneities. So where did they come from? Next, we have the monopole problem. So everyone, I think, has seen this, a magnet. It has a north and a south pole. And sometimes we call this a magnetic dipole. Now, if I take a magnet and crack it in half, what happens? Has anyone done this? You take a magnet and you crack it in half. Who thinks two magnets? Okay. Who thinks two mini magnets will form? Okay. Does anyone think that if you crack it in half, you'll get one north pole, one south pole? No. Okay, good. That was a test. Of course, we've done this. And when you crack a magnet in half, you get two mini magnets. But we know that that's not always what happens. You don't always have poles that just always have to exist together in pairs like this. So for example, with electric charges, sometimes we see positive and negative charges together. Sometimes we see just negative charges. Sometimes we see just positive charges. But we do see electric monopoles. We do see just individual charges on their own. So in fact, the particle physics of the Big Bang tells us that magnetic monopoles should exist. And not only that they exist, but they are created in large abundance at the beginning of the universe. Yet we have never seen a single one in our entire universe. So where are all the monopoles? Next, we have the flatness problem. And this problem has to do with the measurement of flatness. So what does that mean? We measure flatness with the CMB. It's one of the parameters that we can measure. And basically what flatness tells you is something about the geometry of your universe, kind of like what we were talking about earlier, some intrinsic geometry of the universe. So the top image shows a sphere. And this is what we called a closed universe. And in this type of universe, if you were to draw a triangle in this type of universe, the sum of the angles of this triangle are greater than 180 degrees. The second one is what we call an open universe. And if we draw a triangle in this universe, the sum of the angles of the triangle are less than 180 degrees. And at the bottom, we have a flat universe. And in this type of universe, if you draw a triangle, the sum of the angles is exactly 180 degrees. And so we measure with our CMB experiments that we live, in fact, in this type of universe, a flat universe. But we don't just live in any flat universe. We live in a really flat universe. And the physics tells us that if something is flat now after the universe has evolved, that means the initial flatness of the universe had to have been very flat. like basically 100 decimal places precisely flat. No leeway. And so that's kind of a weird thing. And this is what physicists like to call a fine-tuning problem. You can almost imagine if you had two machines that made universes, and you have one, you put in your three initial numbers, you get out a universe, and let's say you make a little mistake, and you accidentally put in a slightly different number. You would think, okay, maybe a similar universe will come out, it's fine. No, it's not fine. You get a completely different universe with a small error. So that's the flatness problem. Next, we have the lithium abundance problem. So the Big Bang theory also has a theory called Big Bang nucleosynthesis. It tells us how we create the first ever nuclei in the universe. And it predicts precisely the abundances of these initial nuclei in our universe. So the Big Bang makes three elements. It makes hydrogen, helium, and lithium. All of the other elements on this periodic table are made, which is really handy, honestly, for this talk. I didn't know this was going to be here, but all of the other elements are made by stars, pretty much, except for some of the weird ones. But the three lightest elements are made by the Big Bang itself. That's pretty cool. And so it predicts that we should have 75% hydrogen, about 25% helium, and 7 times 10 to the negative 8% lithium. So we go out. People have done this. We go out and we measure how much hydrogen do we have in the universe. And we measure 75%. Okay, pretty good prediction. We go out and we measure all the helium. Okay, we measure 25% helium. But then we measure the lithium. And it doesn't quite match. So the Big Bang theory predicts the abundance of hydrogen, helium, and lithium. But we actually see 4 times less lithium than predicted. So where is all the missing lithium? That's the big question. Okay, we're almost done with the problems. So last, we have the naked singularity problem. So if we again go back to our picture of the expanding universe Big Bang model, we have that point, which I said at the beginning was a time when the universe burst into existence from nothing, from an infinitely dense place where the entire universe was smushed into a single point. So that is a singularity, a point of infinite density. And this is not the only place that we know singularities exist. We also have the black hole singularity. So in black holes, they have this, kind of complex geometry where we have in this very center a singularity, but a little bit further out from the very center, we have what's called the event horizon. And that is the surface from which no light can escape. So after you've passed, you've crossed that boundary of the event horizon, the gravity is just so strong that not even light, which is the fastest thing we know of that travels at 300 million meters per second, that is not even fast enough to escape the gravity at the event horizon. But the event horizon does something special because since it doesn't allow anything from inside that region to escape, we can never actually see the singularity. The singularity is hidden or shielded by the event horizon of the black hole. But there's no such concept for the Big Bang singularity. The singularity of the Big Bang is just what we called naked. It's not hidden by the event horizon. And so singularities, some say, well, Roger Penrose would say, he's come up with the cosmic censorship conjecture, which says that singularities need to be hidden by an event horizon. They need to be censored. And there can be no naked singularities. So how could there be a naked Big Bang singularity? And that's the naked singularity problem. Okay, so those are the problems. We have the horizon problem. Not enough time has elapsed between the Big Bang and the release of the CMB for the points at the horizon to be in causal contact. Yet we see them in thermal equilibrium. How? We have the structure formation problem. The Big Bang theory predicts a homogeneous and isotropic universe, yet we observe a universe with inhomogeneities. Where did they come from? We have the monopole problem. The Big Bang predicts that there should be abundant monopoles in our universe, yet we've never seen one. So where are they? We have the flatness problem. If the universe at the time of the Big Bang was even slightly less flat, we would live in a different universe. We have the lithium abundance problem. The Big Bang theory predicts the abundance of the first 3 light elements, yet we find 4 times less lithium than predicted. So where is it? And we have the naked singularity problem, which says that we can have no naked singularities, yet the Big Bang theory tells us that there was one. So now, last but not least, I just want to go over quickly and not in too much detail, 3 possible solutions that attempt to solve some of these problems. So the first one is inflationary cosmology. The next one is Equirotic Cosmology. And the last is cyclic cosmology. So first, inflationary cosmology. What does it say? Is there we can do a question. Or we can do a question at the end. So you can calculate that percentage using something called the Saha equation and some you have these thermodynamic and particle processes, and you can calculate it. And actually, I think for most of us graduate students, or some of us here, that's like one of the first calculations you do as a graduate student studying cosmology. And you get these very precise nuclei abundances. Yeah, good question.
Thank you.
A question from the chat.
Okay, question from the chat.
So could flatness be simply an automatic intrinsic property of the universe, just like the flatness, uniformity, and the line of integer numbers?
So flatness, so the geometry of the universe is an intrinsic property. Why is it an intrinsic property? Because, well, based on our definition earlier, an intrinsic property is a property that people living inside the universe can know about. And if we lived in a universe that was curved instead of flat, or if it was closed or open, those other 2 geometries instead of flat, that is something that we can measure as people, creatures living inside the universe. So yeah, certainly it's an intrinsic property. Okay. Yes, another question.
Problem with the horizon.
Okay.
After the Big Bang, the entire universe is extremely close together. And would have been thermodynamic technology. What would cause it to, where's the problem?
I see.
I don't understand this problem in the problem.
I see the problem you have with this problem. And I guess this kind of comes down to, I'll just go back a few, can I just scroll this way so it'll be faster? So let's go back to this picture with the light cones, and I'll just rephrase kind of the situation that you were describing, which is, if they were all kind of close together. Well, okay, there are two parts of this problem. Just because something is close together does not mean it is currently causally related to that region. So let's think about that. How could that be the case? You can imagine that, and I think we would probably agree that even though this circle describes our observable universe, there's stuff out here. There's more universe. It's infinite. But we don't know about that part of the universe. It hasn't entered our horizon. There has not been enough time for light to come from that region of space to us. Even though this theory posits that all of us were at one point, even the parts out here, were at the Big Bang at the same time. So light is really the limiting factor, because light is the thing that allows us to know information about different parts of space. So that's, I guess, the first part. The second part is then you could say, okay, well, even though these 2 points are not in causal contact, what if you had like little messengers, right? Like you have points all along this horizon. And so what if the red dot communicated with some dot, some other region, some other particle over here, and then over here and over here, whose observable universes do all overlap, right? You can imagine a scenario that solves this problem like by having these messengers. But how do messengers communicate? With light. So by the time the messengers send all of the messages, it takes just as much time and it takes, more time to send all those messages between these regions of space. And that's what's really captured by this observable universe circle that I've depicted here. It's really a fundamental limitation to communicating with portions that are outside of this, of these regions that I've drawn. So our 3 possible solutions. Let's start with inflationary cosmology. So what's the situation in inflationary cosmology? Well, let's zoom in to the very beginning of the universe. And now you can see we've replaced a few things. So now instead of the Big Bang singularity, we have something called quantum fluctuations. And then we've added sort of to the history of our universe a period of rapid expansion called inflation. And this adds just enough expansion to our universe to solve some of the problems. And another portion of this inflationary paradigm is that we kind of like live in this inflationary landscape where there are different regions in this landscape with different sorts of values of fundamental parameters. And when I say landscape here, this is not like a usual space. This is some, abstract space of quantum fluctuations that we have no idea what it is. But for whatever reason, the inflationary model says that a little piece of one of these portions of the landscape expanded in a huge inflation, which then sprung into existence the universe as we know it and started the, evolution of the universe that we are now familiar with. So does it solve some of the problems? Let's see. It solves the horizon problem. How does it do that? Well, it adds to the timeline of the universe such that those 2 regions of space-time there's enough time for them to be in causal contact. It solves the structure formation problem because it posits the existence of these quantum fluctuations, which then appear in the CMB. And those little differences are then what cause the formation of galaxies. It solves the monopole problem because it says that while monopoles are abundant in that inflationary landscape, it inflated it so quickly and spread things out so quickly that it just separated monopoles really far apart, such that the probability of seeing one is pretty much zero. It solves the flatness problem because then you don't have this fine-tuning issue because you come from this whole landscape of possible initial values. The lithium abundance problem, well, it doesn't really say anything about that. I'll say some more about that later. And the singularity problem, well, that's a difficult one because we don't really know what this, initial patch of the inflationary field was. So, question mark. We'll leave that one as a question mark. So the next type of cosmology is Equirotic. And I really like this name because it comes from Stoic philosophy, which means the creation from destruction in fire. So it's exactly what it says. It is the creation of our universe from the destruction of another universe in some hot fiery event. So this is the scenario. It's a collapse and then an expansion. And this scenario is very similar to the cyclic cosmology, so I'm kind of going to group them together. And in this cosmology, you have this collapse and expansion, but infinitely. You have this infinite cycle of collapse and expand, collapse and expand. And it says Big Bang there, but really what a lot of these theories do is they collapse to very small size, but not infinitely small. So you no longer have a singularity. So for these theories, they solve, again, all the usual problems, but they also solve the singularity problem because, as I just described, they don't collapse all the way to the singularity. But as it goes, every model has its own problems, which we're not going to get into today, but this is, the process of science. We had a theory. It's great. It had some problems. We make some improvements. They might have problems. We make some improvements and so on and so forth. So the big question, did the Big Bang really happen? Well, sort of. If you want to call, it is true that 13.8 billion years ago, an extremely important event happened. An event that changed the future of our universe for at least a very long time. And that event is what we call the Big Bang. Is it the expansion from an infinite singularity? We don't know. Is it one of those other theories that I described? We're also not sure. But I think this is a very exciting time to be doing cosmology because there are some really amazing experiments coming up that are going to hopefully elucidate some of these mysteries about the first moments of our universe. And maybe we'll be able to distinguish very soon between at least a subset of our early universe models. And I can't wait. And when we do find out, we'll have a public lecture about it. And you will all be the first to know. So with that, I would be happy to take any questions.
Here? You, yeah.
So
I went to a talk organized by you guys, 10 years ago, like in 2019, and it was a guy who was talking about how stars destroy lithium.
Mhm.
And would that be a reason why there's not as much lithium in the universe as we predicted?
Yes, right. I said I would talk about it, then I forgot. So you might ask, like, why don't these early universe theories like fix the lithium problem if it's a problem that was, originated from a cosmological theory? And it's because most people try to solve the problem astrophysically. So they try to, eat up the lithium through other astrophysical processes like stars. The problem is that we still, even in those calculations, can't quite get them to match, like can't quite get it to all work out. We can't, get enough lithium to be eaten up to account for what we see. So it's still an open problem, but it's most of the solutions are astrophysical solutions. Yeah. There's a question back there in the gray, yeah. You're
the gray, yeah.
What two questions you can stop me with the question. The first one, at the beginning of the lecture, you were talking about the how we measure expansions. So regarding the Hubble constant, what I know is that we can measure that the farther light sources are from us, the longer the wavelengths that come to us. And I have never really got the part where why this implies that the space itself is expanding. Like, why cannot some other thing cause the
red shifting?
Yeah.
Okay, well, first of all, there are multiple sources of red shifting, or the changes in there are multiple. I don't want to say sources. There are multiple kinds of red shifting. There's Doppler red shifting, which is, when you hear a police car go by you, and when something is moving quickly, either towards you or away from you, the waves get stretched. So there's Doppler shifting. There is gravitational red shifting, which is that when you enter or exit a very deep gravitational well, let's say you're some particle trying to get out of this well, when you are climbing out, it requires energy to climb up in this gravitational potential. And so if you had a short wavelength, meaning high energy when you started, you will actually end up losing energy to the gravitational potential. And this is called gravitational redshifting. But then there's cosmological redshifting, which is actually the result of stretching of the universe expanding. And the way that you can think about that is, I said that the galaxies in this balloon universe model were like stickers on the surface of the balloon. So when the balloon inflates, the stickers don't inflate. They're like a separate object that are just stuck on. But light, you can imagine, is like drawn onto the balloon. The way that light behaves in an expanding space, it's like as if the light waves were drawn onto the surface of the balloon, and then when the balloon stretches, that light wavelength also stretches with it.
Okay.
Yeah.
Okay, I think other people have questions. If we have time, we'll come back to you. Yeah, it's okay.
There's
There's one
Emily?
here.
So I think you related determining that the universe is pretty flat to the cosmic microwave background. I'm wondering how
we do
those are
that.
linked. Yeah.
Okay. I feel like Adrian is laughing at the back because it's actually a really complicated measurement. So I will try to explain this. I will try my best to explain this. So when we look at this cosmic microwave background, and I actually had a plan to talk about how we actually make these measurements with the CMB for another public talk, but it's going to be hard. But basically what we do is we make a special, we compress this data into a way that's easier to see, I guess. So you can see that in this map, there are kind of like big scale features, right? You can see that if you kind of like blur your eyes a bit, you can see there's like one big red blob here, a big blue blob here, another big red blob. And then if you like unblur your eyes a little bit more, you can see there's like this size blob red over here, and then like this size blob blue. And then if you like zoom in a little more, you have like all of these different scales of fluctuation, like depending on how blurry your vision is. And so what we try to study using statistics, and I feel like this is where I might lose people, but we have a special statistic called the power spectrum. And if some, I know that some of you were here at last month's public talk where Adelie explained this, where we actually make a plot with like how much big blobs there are and how much small blobs there are and how many little blobs there are. And it looks like this. If we make a plot of the blobs, and over here, we have big blobs. And over here, we have small blobs. This curve is predicted theoretically, like the exact shape of this curve. And this curve depends on that flatness parameter, which we call K. The K we call the flatness parameter. And it turns out that changing the flatness will change the distribution of the blob. So like, we'll get a different shape of blob size. We'll get a different abundance of blob sizes in the CMB. And that's actually how we measure the abundance of matter, the abundance of dark matter, the abundance of cosmological, dark energy. That's how we measure everything, well, not everything, but that's how we measure our fundamental cosmological parameters with the CMB, is by studying its statistics and, looking at the amount of different sizes of blobs. Yeah.
Isn't this statistically homogeneous?
So large scale, yeah, that's why we see, if we, calculate the mean, we'll get this. But then if we compute the variance
That are very small.
that are very small, that's how we get the blobs, the statistics of the blobs. So we have these small deviations that are, I guess, local, which then end up eventually causing a little bit more matter to be in some places than others. This distribution of hot spots and cold spots then tells you what the distribution of matter is in the universe. And these slight deviations in slightly denser spots in the universe and slightly less dense spots very early on, due to gravity, eventually become huge galaxies and large voids. So yeah, from something pretty much homogeneous and isotropic, we get, these dense galaxies with billions of stars. And then, the cosmic void, which has like an average density of less than 1 atom per cubic meter.
You didn't talk about the baryonic acoustic oscillation. Where you place position that into the top, maybe.
If ever. These are the baryon acoustic oscillations. So how do I put this? Let's go back. What are they? What are the baryon acoustic oscillations? Funny word. Okay. We're back in the early universe. We're back in the time of the plasma, before light could pass free. And here, I'm just depicting atoms, or sorry, they're not atoms yet. They're nuclei, electrons, photons, but also in this soup is dark matter. But the dark matter doesn't interact with light, so it's not participating in this plasma. So it's kind of but it does know about those fluctuations. So the dark matter starts clumping together and starts to form slightly denser regions and slightly less dense regions. But this plasma is oscillating. This soup of stuff keeps oscillating in this early universe. But then, so you can kind of imagine that, you have these dark matter peaks that are, the dark matter is starting to clump together because it doesn't know about light. It can't participate in the plasma. But then you have all of these particles that are still, swimming around, and they kind of ebb in and ebb out and ebb in and ebb out, as if, when you drop a stone in a pond. And eventually, the universe expands enough to let the photons free and to form atoms. And at that instant, the plasma doesn't exist anymore. And so the plasma is not oscillating because it doesn't exist. And so wherever the plasma was at its last oscillation, you end up, so now let's do a top-down view. You have this like dark matter overdense part, but then you froze in the atoms at a certain location around the dark matter. And what this ends up doing, and we can see that by studying the statistics of this. So, you can't see it by eye here, but really hidden in this are these sorts of shapes where you have slightly denser rings around a very dense core. And it turns out that when you do the conversion of this type of map into this statistic, you see these oscillating features, which is basically some weird way that we mathematically depict this sort of shape. And we do see this even in the sky, in the distribution of galaxies. If we go out and measure and look at where all the galaxies are, we will literally see little galaxies, a bunch of them close together usually, and then we won't see a lot. And then we start to see a ring of galaxies around. It permanently, this last oscillation of the baryons of the regular matter got frozen in and embossed permanently into the distribution of galaxies in the universe. So yes, the baryon acoustic oscillations are certainly a super important part of studying this early universe map because it had consequences for all of galaxy formation later on. Yes.
We have.
So, how would we know when exactly the light would form in reference to the singularity or when the Big Bang happened? How do we know when that actually would show up? Because if we're using light as a measurement to see the oldest things in the universe, how do we see before that?
So you mean, how do we get from the CMB to the singularity? Well, you basically have to believe that the physics that that must have created the CMB was still the physics governing from the singularity to the CMB. And we have good reason to believe that, because the creation of the light elements, hydrogen, helium, and lithium, actually happened before the CMB. It happened in the plasma before we could see into it. And we still, using the physics we know, I mean, apart from the lithium problem, but that's an astrophysically, that's a problem that will likely be solved astrophysically. We have good reason to believe that the physics that we are familiar with still holds during that period between the Big Bang and the CMB. And so because we know the CMB, based on our theory, should have been 400,000 years after the Big Bang, then we know the Big Bang had to be, 400,000 years before that. Yeah. But again, we don't know. It's the Big Bang on its own did not happen. Like, that definitely did not happen. There is something else to the story that we're not sure exactly what it is, but in almost all of the early universe scenarios, they do kind of posit, maybe not in the usual way we like to think about it, but some sort of like before time, or some sort of state of the universe before the Big Bang event, whatever it was. Oh yes, wait, we have one question online, and then
So we have, could inflation and expansion both be a consequence of our not fully understanding light and its interaction with spacetime? If I'm correct, expansion and acceleration was meant to explain redshift. So that's a red flag to me that we're trying to explain too much too early. Though it's still the coolest topic.
wait, can you explain the last part again? Could you read
That's
the
just a
last part?
comment, okay. If I'm correct, expansion / acceleration was meant to explain redshift. So that's a red flag to me that we're trying to explain too much too early.
I'm not sure I fully understand the question.
Basically, could inflation and expansion be a consequence of our not fully understanding how light interacts?
How
with
light,
spacetime?
okay, could it just be completely a misunderstanding with light?
Yeah.
Well, I think that would be difficult to say that we don't understand light to that degree, because we can see the redshift of light very clearly in the spectroscopy that we take with with telescopes. We actually see every element emits kind of like a specific barcode. It emits a very particular spectral shape. It emits as a function of energy or frequency. It emits very specific energies or frequencies, which are in some particular orientation or shape that is for that atom only. And so when we go and look at other galaxies, we see that exact shape shifting, red shifting, going to lower energies, but the shape is intact. So I think it would be very difficult to claim that we don't know how light and red shifting works when we see very strong evidence of red shifting in spectra. I'm speaking from the point of view of someone studying cosmology, but the properties of light enter in all areas of physics. So you'd have to break a lot of things to say that we don't understand light, like a lot of things, like all of our internet, like all the fiber optic cables. We would have to say that we don't understand what light is enough to make all of our infrastructures with electricity work. So I think that would be a very hard claim to make.
The question.
Oh wait, there was one
Oh,
question.
there's one.
What? Yes, I see you were waiting for it.
Okay, so it's about the singularity problem.
Mhm.
Like, why must there have an event horizon? Like, you mentioned a theory that like ruled out the Big Bang because there wasn't an event horizon around singularity. Why must there be an event horizon hiding singularity for it to be singularity?
So-
Here's the question.
Why, okay, so so the question was, why does the singularity have to be hidden? Like, why can't it just be naked? Like, why is that really a problem? And that, I think that really depends on who you ask. Like, there are some theories that allow naked singularities. Yeah, there are some that allow for it. But I guess maybe not traditionally, but I guess earlier on, naked singularities were, I guess, not aesthetically pleasing for the theorists. There are a lot of like aesthetic things. And I mean, there are like, you know, more profound motivations too, but there are theorists who do work on theories that allow for that.
Okay, very short, simple question
Okay,
about your diagrams.
okay.
Three of them seem to be quite compatible, but some of the others didn't seem to be compatible, seem to cancel each other out. But the three that I thought were very similar, last one was your illustration of the alternately expanding and contracting.
Mhm.
And compatible with that was the first one you showed us, or two of them were like the universe was like a test tube on its side with a big bang at one end and which a day at the other end, bright light at one end and
Mhm.
big bang. Yes,
Mhm.
and there was another one that's not quite the same, but those three seem to be compatible with each other. But although they're very far removed from anything I can find similar to common sense, but something more closer to common sense would be a sphere, a circle on the screen, where we're at the center.
Mhm.
We are at the center, and at the outside is the limit of our telescope, telescope's capacity.
Mhm.
Okay? Now, you don't need to show us the circle, everybody can understand. Where on that very common sense picture of the universe, of the sphere, of the circle, where would the Big Bang fit into that?
Okay.
Would it be
So,
the middle?
no,
Would it be the
no,
most obvious?
no. So, okay, the difficulty is that I see your question. So I think, let me see if I understand your question. So you would like to know if we see the Big Bang happening at the edge of our universe, right? At the edge of the circle.
Yes.
Then how could the Big Bang have happened everywhere? That's really the crux of the question, right? So, and I remember this because I really thought hard about our discussion last month. Because, and it really got me thinking, and it honestly inspired a lot of this talk. And I understand now, maybe you will let me know how to perhaps explain this. So first, let me tell you what the CMB is and is not. The CMB is not a picture of the entire universe's Big Bang. What the CMB is we are watching a little shell of the universe experiencing the Big Bang. That's not the whole universe's Big Bang. Why? Well, because as I said, light is like a time machine, which means that we can see the past elsewhere, but we can't see the past where we are. We can only see the present where we are. And so kind of your question is like, how could it possibly be that we're both looking at our Big Bang, but also we're here in the present? And the answer is we're not. We're not looking at our patch of the universe going through the Big Bang. So just like, I'm just going to bring up this image here. So we are, from an observer's point of view, we are at the center. If we look out some distance, maybe we see what a little shell of the universe looked like 100 years ago. We can't see what our patch of the universe looked like 100 years ago. We can't see what 4 light years looked like 100 years ago because, you know, we're only 4 light years away. And likewise, when we look very deep out into the universe, we are only seeing what a very small portion of the universe looked like at the Big Bang. We are not seeing the whole universe experiencing the Big Bang. So when we have these other models of the universe, the test tube model, like you put it, now we are we're no longer placing ourselves at the center of the universe. Now we're kind of stepping outside of the universe and looking at all of it, including our little patch, including the parts that are 100 light years away, 1 billion light years away. We're looking at it as if from the outside, and we're drawing this history. But the assumption is that this same history, you know, happened everywhere, even though we can only take samples from different patches due to the speed of light. Yeah. I hope that answers your question a little bit more.
Not at all, but I.
Well, we try. But maybe we can continue again. Okay. Do we have time for 2 more?
Yeah, let's
3
do
more? 3 more? There are 3
No,
more.
it's already 8:30 almost.
Okay, yeah, at the very back.
How far back can you see right now with the latest CJs?
Well, okay, well, that's kind of difficult, like how far back, because we can see here, and we've been seeing here for a while. But it's actually a very difficult part to see is this. The huge chunk in the middle where it's just because of the physics and because of the stuff that's going on, like it is very hard to see. The CMB is a really special thing because even though it's very far away, we have a very strong prediction for what it should look like. So then we can build telescopes that exactly look for what we want to see. But here it's like the universe gets complicated here. Like the physics here is very simple, thermodynamics and some particle physics that we know. But then here it's like you have gravity, you have particles, you have galaxy assembly, you have stars bursting, you have things exploding, you have black holes, like it's crazy. So, so this part, it's really tough to see, but with James Webb, we started to see a few galaxies from this first population. And actually, so the area that I work in is studying basically from the dark ages to the end of what we call cosmic dawn and reionization. So cosmic dawn, as the name would suggest, is when the first stars turn on, when cosmically it's dawn. And so, yeah, I work in this area where we try to observe here. And then, you know, this is like later times is then again gets then easier to observe.
Super fast. Why is the little corner of the diagram lifting up that?
Oh, so I think this corner of the diagram is showing both. So the purple stuff is like the cosmic web, which shows the luminous matter and the dark matter. And then when you peel it, you just see the luminous matter. Yeah.
Yeah, okay, let's
Okay,
go.
yeah, go ahead. Yeah.
How is inflation a solution when it itself is built on? Okay, we've got these problems. Maybe inflation is the solution, but you've got faster than light expansion, which begins at a certain point and ends seemingly just completely everything. And we aren't in a period of inflation now.
Nope.
Why would it start? Why would it stop? So,
Well, so inflation, so I mean, well. So,
And every solution was.
yeah, so I mean, inflation is kind of an interesting theory because it's one that has a lot of freedom from the theorist's perspective to tune knobs and adjust the theory as need be. So, you know, if you look at inflationary theory, there's like almost maybe even infinitely many theories. They're not all viable anymore. We've ruled out a good portion of them, but there's a lot of possible inflationary scenarios that you can write down. And the ones that you can write down or that people have written down, you can basically, you kind of end up with a fine-tuning problem all over again, where you have just enough inflationary expansion and you cut it off just so that you know, end up with the same universe that we have now, and you solve the horizon problem and you solve all these things. But I mean, inflation is still, from a theoretical perspective, even though it has its own fine-tuning problems, it's very impressive that it doesn't break anything. So it doesn't break anything that we already know about the universe, and that's difficult in its own right. But yeah.
Its origins.
Yeah, so we don't understand the physics of okay, we don't know what caused inflation. We think it was some quantum field. All the fields we know about we know, we've checked, they are not the right fields that produce enough inflation for our universe. So every particle we know about cannot be the inflationary particle that creates this field from which we emerge. So yeah, it's also a problematic theory because it imposes physics that we don't know. So I think your concern is very justified, and I have the same concerns.
Okay, well, please join me in thanking Hannah for and thank you all for coming. Do you want to do the raffle, or
Oh yeah, we have raffle.
did anybody enter their names in the raffle? Yes, okay.
If only 2 people enter, then come get your.
We didn't have a few on.
Oh, people not have enough time to do it.
It's fine. If you filled it out, come to us.
17.
Best we've also had to leave enter her name.
I totally asked yeah,
Like, why? I don't know if I just missed it, but why?
well, so the monopoles that the monopoles that are created in the early universe are actually not the exact same as like the magnetic monopoles that we heard about in electromagnetism. They're something called topological defects. They're like these weird little like peaks in space-time where you trap. That happens because parts of trapping energy, because in the early universe when things are evolving very rapidly, you go through like phase transitions, like you know when water, like the water evaporates or something.
Yeah.
Yeah,
It does. No, it does. And there are entire lectures that we have gone. Weird stuff. Yeah. So yeah, these monopoles are like little trapped pieces of energy. And they behave analogously to the magnetic monopoles. They do have magnetic properties. And so because these fluctuations cause these trappings of energy, everything's a little, and kind of have you ever